Hello everyone, welcome to my channel. In this series, I would like to demonstrate those questions that most frequently asked or most often appeared in A-level math exams. And in this particular video, I would like to show you a particular standard question about how to find the area bounded by intersection of curves and probably one of the axes, okay? So let's now begin. Figure 2 shows a sketch of part of the curve C with equation y is x times natural log of x greater than 0. The line L is normal to C at a point P, E, E. The region R shown shaded in figure 2 is bounded by the curve C, the line L and x-axis. Show that the exact area of R is AE squared plus B, where A and B are rational numbers to be defined. So for this particular question, you might wonder what's our starting point? Well, because it asks us to find the area in the graph, it's most likely we're going to use integration, as also suggested by the title. It's one of the integration problems. So for any particular integration, the first thing you're going to ask yourself is, do we know the upper and lower bounds? And do we know the function that we're dealing with? For this particular question, you can see, obviously, R is not such nice shaded or very rational or regular shapes. You can't just, it's not a triangle, so you can't just use triangle formulas, and because it's bounded by two different graphs. So the main reason I choose this question because it shows how typically you'd have to divide the region R into two distinct parts. And I say I should divide R into 1 and 2. Why is so? Because you can see for 1, you can describe by a single interval between, let's call it A, B, and C. Okay, so for area 1, you can see it can be expressed as a single integral from A to B by the curve C. And for region 2, you can express as a single integral between B and C bounded by the line L and x-axis. Okay. So our main strategy here is, first of all, splitting the graphs into the two parts, and then find the bounds A, B, C respectively. We shall start with A. How do we find A then? Well, you can see it's an intersection with the graph of x, with the graph of C and x-axis. So that suggests at A, y equivalent to x natural log of x is 0. That suggests two possibilities. X is 0 or natural log of x is 0. We know that x is greater than 0, so it can't be this possibility. It must be that natural log of x is 0, and that implies x is 1. Right? We know that natural log of 1 is 0 because exponential of 0 is 1. Cool. So we now know that A is 1. And now let's determine B. As suggested by the graph, B tells you straight away, B is a point E, 0, right? Because it's basically vertical projection from P onto the x-axis. So B, as it's the vertical projection of P onto x-axis. So B is E. And for our last thing, we're going to find C. How do we find C? So first of all, we shall think about what is special about C. Well, you can see it's an intersection between the x-axis and the line L. And we might be interested in finding the equation for L so we can determine the x-intersection. So how can we do it then? First of all, find equation for L. And how can we do so? Well, we can see that very useful information here. Line L is normal to C at a point P, E, E. So we need to find the normal to the curve C. And to find the normal of a curve, we then need to find the gradient of L. Normal, we know that normal, the gradient of a normal line times the gradient of a tangent line is -1 always. So now we shall find gradient of curve C at P. E. Cool. So y is x natural log of x, and dy dx will be, well, we shall use product rule here because x times natural log of x. So natural log of x plus, because differentiate x first, and then differentiate natural log of x, we have x over x, which is natural log of x plus 1. And find dy dx at x is e. It's basically natural log of e plus 1, which is 2. So that suggests the gradient of L would be -1/2 from the relationship between the gradient of tangent and the gradient of normal. Okay. So we may summarize that equation for L is in the form of y is -1/2 x plus some constant k. And we know that EE is a solution of this particular line. So E is a -1/2 E plus K. Alright, that suggests K is 3/2E. So L is y is -1/2 x plus 3/2E. Brilliant. So now that suggests when y is 0, equivalent to -1/2 x plus 3/2E, that suggests x is 3e. So C is 3e. 1e, 3e. Now we might find the area of 1 and 2. So how are we going to find area of 1? Well, as I said, it's a single integral from a to b. So 1 to e of the curve C, x natural log of x dx. How are we going to do so? Well, I think because there's a product here, so we shall use the integration by parts, shall we? Let's take u to be natural log of x, then du dx is 1/x, and let's dv dx to be x, then v is 1/2 x squared. Brilliant. So by our formula, we know that the integral will be 1/2 x squared natural log of x between e and 1 minus the integral between e and 1 of 1/2 x squared over x. So uv is the integral value here, and du dx times v is the integral we need to calculate next. Oops. Let's just calculate the bracket here first. So that's 1/2 e squared times natural log of e, which is 1, minus 1/2 times natural log of 1, which is 0. So that's basically 1/2 e squared minus integral of 1/2 x squared x. So that's basically the integral of minus 1/2 x. So that shall be 1/4 times x squared, right? Between e and 1. That is 1/2 e squared minus 1/4 e squared minus, so plus 1/4. We shall have 1/4 e squared plus 1/4 as the area of 1. Now for area of 2, can move something around here. Now we have enough space, sorry. Poorly organized. So area of 2. Let's just observe the graph carefully. Because we know that 2 is an area under the line L, so that means it's a triangle. Okay? You can see the height is E. Height is E, and the base is 3e minus c, so the base is 2e, and by our triangle formula, we can notice that, well, obviously, the area is a half times base times height, which is e squared, so area of 2 is e squared. Now what we need to do is area of 1 sum area of 2, which is 1 over 4 e squared plus 1 over 4 plus e squared, and now we shall have 5 over 4 e squared plus 1 over 4. Exactly as required, because we know 5 over 4 is rational, 1 over 4 is also rational. Okay, so the area is 5 over 4 plus 1 over 4. Brilliant. So for this particular question, it's just two standards. You can see because we have two different graphs intersecting here, and the whole bounded closed interval cannot be described as a single integration. So to deal with that, we just split into different, a couple of integrals maybe. In this case, we need to split into two. And how we split it is usually quite standard, because you may assume that if we split in two parts, then the endpoints A and C in this case would be where they intersect the axes. So in this case, they intersect with x-axis, the lower bound and upper bound. And for the intersection of the partition in the middle, where it should be, that is usually where it's usually the vertical projection of the point where the two lines intersect. I think it's kind of reasonable, because at the point of which two lines are intersected, you can't have like a unique and continuous integral. That's why you're going to split at exactly where the lines intersect. Okay, so you can have two uniform and two continuous functions they can integrate in one whole. Okay, this question you can see is a 10 marker. It's definitely difficult. Okay, to complete this question, you can see it follows a very rigorous logic. Okay, what is my aim? And to achieve the aim, what I need to do next, and you can see it just follows like to achieve the next thing I want is set a strategy for what I want to solve for next, and eventually this gives you a starting point. If you're first to these kind of questions, you will be obviously confused, because it just doesn't look approachable at all. And that's the point I want to mention, because no question does seem easy at first. But once you do practice more, you will just be familiarized how they are structured, and you're familiarized with the kinds of arguments or the strategy or the logic. And to that point, you'll find that, well, every starting point or every progress, any process, will just seem to be reasonable enough that it has to be that way. Okay, you'll be used to these type of questions after many practice, definitely. So yes, okay. It's not just enough to watch me to complete this question for you, and it's vital for you to complete those type of questions many times yourself. And I think that'll be it for today. Hopefully you have learned something useful from this video, and see you next one. Bye bye.